Okay, so we are into chapter 8 now. And the first thing we're going to do, actually today, really what we're going to do is kind of review our combinational circuit design procedure, right? So we've spent the whole class so far just kind of learning different techniques for designing our circuits, right? We've sort of added to the procedure as we've gone along. We've added new detail and we've accounted for new edge cases. So what I want to do for the first half of this class is we're just going to kind of recap and sort of get a picture of what our universe kind of looks like. What are the steps involved? What are the things that we have to do in order to design our circuits? So we'll just call this a review of combinational circuit design. All right. So, what are the steps? Step 1 is get our truth table. So we're going to say step 1 is set up a truth table. Specify the circuit's outputs for given input combinations. Here we're basically saying you start by figuring out what it is that you want to do, right? We want to build a circuit that takes these inputs and gives these outputs. And we're going to define what those are by putting them all into a truth table. That's where we'll start. Step 2 is use the truth table to derive expressions, or excuse me, to derive the generalized min-term or max-term expansions. Right, that is the f is the sum of min-terms 0, 1, 3, so on and so forth, or it's a product of max terms 2, 7, 12, so on and so forth, right? So you're going to take the truth table, look at all the rows where you got 1s and 0s, right, and put in those values for, or get your expressions for your generalized min-term or your max term expansions. Again, depending on if you want to get a sum of products or a product of sums. Step 3 is plot the min-term, max-term expansions on a K-map and use the map to find the minimum sum of products or product of sums expressions, Boolean expressions. So, take your min-term, maximum expansion, stick them to K-map, do your loops, do your groups, figure out what your minimum expressions are. Step 4 is draw the two-level and or and logic circuit. Now you could stop here, right? Because this gets you a working logic circuit that is largely optimized, right? You got it most of the way to your optimized solution. Anything you do beyond that is going to be sort of just degrees of optimization. And so you've got a working logic circuit here. So we'll take our next two steps, 5 and 6, we're going to say that they're optional. So step 5, we'll call it optional, is factor or multiply out the Boolean expression to get a multi-level circuit of and or. Right. This is where we showed that if you took even your minimum expression, if you did a little bit of factoring, a little bit of multiplying out, you could get a circuit that had multiple levels, but maybe those multiple levels might have fewer gate inputs than even just the minimum sum of product or product of sums solution. And in step 6, also optional, although less optional than step 5, is convert your logic circuit to a circuit of NAND gates or NOR gates. And remember that this is because in practice, NAND gates and NOR gates are smaller, they're cheaper to build, they're more fast than AND gates or OR gates, right? So it's always a good idea to convert your circuit to NAND gates if you're actually going to build the thing physically on some silicon, right? So this is where the world looks like for us right now. Just to kind of recap, step 1, we're always going to start with the truth table that lays out here are all the inputs and these are the outputs that we want for those inputs. You're going to use that truth table to get that minterm or max term expansion, sum of minterms 0, 1, 3, and so on, or the product of max terms 2, 7, 12, so on. Then you're going to take those expansions, you're going to drop them into a K-map and use that K-map to get your groups, to do your groupings and get your minimum sum of products or product of sum Boolean expressions. Once you have that, then you can draw your two-level and or AND logic circuit, and you could stop there because that's going to get you a working logic circuit that does the thing that you need it to do. Step 5 is optional. If you can get a more optimized solution by factoring out or multiplying your circuit to get multiple levels but fewer gate inputs, you should do that. And then 6, also optional but less optional, you should probably go ahead and do this because it's just good practice, is to convert your logic circuits to circuits of NAND gates or NOR gates, right? Because you're going to sort of squeeze higher clock speeds, more power efficiency and stuff like that out of your NAND gates than you would out of your AND gates or OR gates. So this is our process for digital systems design as it stands today. Are there any questions about that? About the process? Well, we can do some pretty sophisticated stuff with the process that we have already. So, okay. So chapter 8 is really all about ways that this process doesn't work. Limitations, weird quirks that come up that might sort of throw a wrench in this process and that we have to deal with. So the first one we're going to talk about is a limitation called limited fan-in. Limited fan-in. Let's go ahead and define what we mean by fan-in really quickly. So definition, fan-in, it's the maximum number of inputs allowed for each gate in a logic circuit. So fan-in, the maximum number of inputs allowed for each logic gate in a circuit. So if I have an expression like, say this, we'll say F is equal to A or C prime or B, C, D, or A, B prime, C prime, D, something like that. And I go ahead and draw this. Now this is a sum of products expression, which means we're going to get a two-level and or logic circuit. So we get AND gate, and AND gate, and AND gate. First one has A and C prime. Second one has B, C, and D. Third one has A, B prime, C prime, D, and they all feed into an OR gate and gives us our function F. If we make a note of how many inputs to each logic gate, this first one has 2 inputs, the second one has 3 inputs, the third one has 4 inputs, and this OR gate itself also has 3 inputs. So we would say that the circuit here has a fan-in equal to 4. Whatever the highest number is the fan-in of that circuit. And it turns out that due to a number of constraints related to the realities of actually building these circuits in a factory, depending on the technology that you're using to realize or implement your logic, depending on the types of transistors, the node size, right? You may have heard things like 4 nanometer versus 6 nanometer, right? Depending on those sorts of factors that go into working in the factory, maybe the factory is only machined for designing 2 input NAND gates or something like that, right? There are a number of reasons why you might be faced with a limitation that says you can only have gates of a certain fan-in or logic circuits of a certain fan-in. And you've got to deal with that. So for example, you might be faced with a problem like this, which says, realize F is a function of A, B, C, and D, which is equal to the sum of minterms, 0, 3, 5, 8, 9, 10, 14, and 15. So there's your spec. Using 3 input NOR gates. So you've gone to work for a semiconductor company, you're an ASIC designer. ASIC stands for Application Specific Integrated Circuit. And they say, hey, we want you to design a circuit that does this, and the fab we're going to use is geared up for 3 input NOR gates. So design the circuit, right? That's the scenario. This is a very, very real world type thing that you would face if you were an ASIC designer at a semiconductor company. So let's go ahead and do it, right? So we've kind of skipped over step 1, right? We've gone straight to step 2. We have our minterm expansion. There are a couple of points here, right? The first one is that we're dealing with 3 input logic gates. We have a limit, we have a fan-in constraint, which says that we can only have 3 input logic gates. And we also are told that we have to design our circuit using NOR gates. And that's going to affect our decision making right off the bat, because to make our circuit out of NOR gates, what do we have to start with? Do we remember? Flip it over. The other one. Yeah, so we got to have product of sums, or more specifically, if we want NOR gates, remember we have to have a circuit that ends, the final level has to be an AND gate, right? Which means that we're going to do it in product of sums, which means that we're going to do our K-map with the zeros instead of the ones, right? So the fact that we want to end with NOR gates sort of informs our decision-making process even at the very beginning. So let's do it. So this is a 4-variable circuit, so we're going to make 4-variable K-map. Oh, I screwed that up. Four. I tell you, this is my last class of the day, and my tablet just like can't handle it. I need to remember to like reboot it before this class starts. Or actually, what I really need, here's this. I give this as an extra credit thing, a standing extra credit opportunity. What I really need is in my shapes palette here, I need like the basic stuff. Oh no. It's because I complained about it. I'm going to mark the time. 1:22. That's when it went out again. Okay. Wait, maybe it came back. Well, this thing crashed all the way out. Hey, bear with me real quick. We're going to take... I'll be right back. I'm going to see if that classroom 2 over is being used right now. We might move for the rest of the day. All right, gang. We're going to move real fast over to 77. It's the classroom at the end of this hallway. It's the one that's got a chalkboard. All right, folks on Discord, we're going to take a momentary intermission.
Are you having trouble with that?
Yeah, you know, during like every other class, like in the middle of class, it like...
Because I'm supposed to check it right now. Maybe I could help you unless you just want to move.
let me do that for today, if you don't mind. Yeah, like every other class, it breaks down. Kind of like it is right now.
HDMI?
Yeah.
Okay, I'll check it right now.
Okay.
Thanks
Thank
for
you.
telling me.
No problem. Thank you for just being around and taking a look at it.
Yeah, of course.
I see now that it may have come back, but it's been a pretty systemic problem. Like it happens all the time.
Okay, good to know. I'll definitely make note of that.
thanks for getting set back up real fast. Don't you anymore. Don't you. And you. Not that. This is kind of great too, because if I'm being honest, I kind of enjoy teaching off the chalkboard than the tablet. So. It says it's recording, but I don't believe it. Let's see, you guys are getting along. Let's see. Back, menu. Pop the screen up. Do that. Go live. Right. Thankfully, we hadn't really gotten into this problem yet. So, all right. Any questions before we kick things off again? All right. That's fun. Okay. So let's kind of roll back just a little bit. We'll kind of see what we started with here. So remember, we're trying to realize this function f, which is a Boolean function of 4 variables, is equal to the sum of minterms 0, 3, 4, 5, 8, 9, 10, 14, and 15. Using free input. Free input is our fan-in constraint, NOR gates. And a technology constraint, we have to use NOR gates. And we know that we're going to start off by using a 4-variable K-map. So let's go ahead and set that up. Let's see, we got F, we got A, B, C, and D, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0. 0, 1, 1, 1, 1, 0, and then we're going to drop in our values from our midterm expansion. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. All right. So first off, are there any questions about how we set up payment?
You just switch from. Was there always a 4 in there?
Yes.
Okay, I guess I'm just.
Did I forget the 4 over there?
Yeah.
Okay. Well, yeah, it's got a 4.
Shouldn't 14 and 15 be 1?
No, you're absolutely right. Since I counted wrong. 12, 13, 14, 15. There. All right. Any other questions about how we set this up? Make sure I'm paying attention to these guys. Okay, so since we want to find or build our circuit out of NOR gates, that means we need to build a circuit that ends with an AND gate. It means that we're going to use product of sums. It means that we're going to group what?
Zeros.
Zeros. Good. So we're going to start by grouping the zeros. So let's kind of just dig into it, right? Start with the big expressions. So that 1, 0 is kind of by itself, has no adjacent terms. You look so bored, man. You okay? You doing some more of the monster? What? You're just like sleeping in your chair, man. Just stand up and do some jumping jacks. Alright. So let's see. We got F. So what does this get us? It's 0. It's a max term. It's in 0, 0, 0, 1. Means we're gonna have what?
A naught, B naught, C naught? No.
Good. Yeah, remember it's flipped over because we're doing the max terms. So 0, 0, 0, 1 is going to get us A or B or C or D prime. Grab this one next since it's also by itself. So that's a max term at 1, 0, 1, 1. So it's going to be A prime, B, C prime, D prime. So yeah, we got and A prime or B, yeah, or C prime or D prime. All right. Now we can make some groups of 2, right? So here, let's have this one. It's at 1, 1, so it's going to be A prime, B prime. Then it's at C equals 0, so A prime, B prime, C. So A prime, or B prime, or C. And then we've got another group down here. And that's going to be at 0, 1, 1 dash. So it's going to be A, B prime, or C prime. A or B prime or C prime. And finally, I think, this one. It's got A equals 0, which would be A or C prime or D. There we go. All right. So, any questions about how we use the K-map to set up our minimum product of sums expression? So, we got some problems, right? Can we just go ahead and build this, or even convert it to NOR gates yet? See some shaking of heads, why not?
You need to simplify the 3 inputs.
What's that?
You need to simplify the 3 term.
Yeah, we need to simplify. We got some, we got a lot more than 3 inputs in some of these places. The first one that immediately jumps to mind should be these 2, right? Because they're both 4 input OR gates. We got to bring them down to something. So what do we do? So remember, we can't simplify it using the uniting theorem, right? Because we already have a minimum product of sums. So we're not going to make it any more minimum than it is. What we have to do is change the form in order to get the sort of number of inputs that we're looking for. So what we need to do is either factor or multiply out. In this case, we want to factor.
you factor B out of it?
What's that?
Would you factor B?
Saying from here, speed?
Yes, since that's the common term. or
Yeah, well, it's not the only common term, is it?
You can use D or D prime and C
Oh,
or
Yeah.
D or D prime and A or C or A prime or C prime.
You're on the right track.
No.
So the formula, remember this, x or y, and x or z, is equal to x or y z. This is the formula we want to use in these cases. In which case, now, we're going to say let x equal what?
B or D prime?
B or d prime. Which means y is going to be
A. Or no,
not just a,
C. Or C.
yeah, a or c, and z is equal to
A prime and C prime.
good, a prime or c prime. So that means that these two terms are going to combine to give us this. What, b or d prime or a or c and a prime or c prime. And then the rest of it. A prime or b prime or c, a or b prime or c prime, and a or c prime or d. All right, so this is good, right? Everything has been brought down to less than 3 inputs, right? Fanning says it's the maximum, but you can always have less than that. So we have 2 inputs. Together they give us, you know, if we did the tree diagram, we have 2, and those all get ORed with, oops, excuse me, they're on one level. And AND them. And then they get ORed for 3, so that's all good. But we're not quite done yet. Why?
Because you still have a product of, some product, no product of some.
Well, the form is correct. That's fine. We still have an AND gate on the outside. Let's see if we finish this up, right? This last level of OR gates right here is going to match with these guys. So that's going to be 3, 3, 3. And then the last level is the AND operation that happens. What's the problem? Problem is that it has 4 inputs. All right, and we're still limited because that's going to get converted. That last AND gate is going to get converted to an OR gate as well. It also has to be at least, or it can't be more than 3 inputs. Which means we got to eliminate one of those other terms to bring the number of AND inputs down. So what can we do?
What you do there? A plus
Could
C
you,
prime.
A or C prime? Okay, what would you get?
Do it.
Can I erase this tree diagram? Give us some room to work on. Alright. Yeah, you're absolutely right. We're going to do the same thing that we just did. But we're going to do it here with A or C prime, A or C prime. So I'm going to fill in the rest of everything. B or D prime, or A or C, A prime, C prime. And this guy's going to stay the same, A prime or B prime over C. And then these two terms are going to convert or combine to give us A or C prime or B prime D. Does that make sense? We just apply that second distributive property to those last two terms using x is equal to A or C prime, y is equal to B prime, z is equal to D. So we go back and draw our tree diagram again. Alright, some stuff is the same. That's two. Then I'm going to AND these guys. That's one. And also, since remember everything's going to be on the same gates on the same levels, let me go ahead and take advantage of the time to do the AND operation there. And then I'm going to do my ORs. That's 3. That's 3. That's 3. And then finally, I end up with that last gate is 3. So we had a level of OR, a level of AND, a level of OR, and we ended up with a level of AND at the very end, and no gate having input greater than 3. So all is well in the world, right? Now we're ready to build it. I'm going to erase this left-handed side here and give us some room to build on. So we'll start by implementing it as it's written, right? We'll lay out all the AND gates and OR gates and get a sense of the topology of the circuit. Alright, so let's start. So the last back-end level is going to be those OR operations. So we're going to have an OR gate with A and C, an OR gate with A prime and C prime. The next level is our AND level. That was these two. And down there at the end, the B prime and D. And those fed into an OR. Let's see. We had how many OR gates? 3 OR gates. That would be 3. An OR gate which took the result of that AND operation and B or D. Another OR gate that was, let's do the one for this AND operation. So that was B prime and D or A or C prime. And we finally had an OR operation that was all on its own, A prime or B prime or C. All right, and then they all get ANDed together, right? 3 inputs into an AND gate. And that gets us our output function F. And the only thing left to do now is convert it to OR gates. Let's make a note of our levels. That's level 1. That's level 2. That's level 3. And that's level 4. Alright. Can I erase this right now? Because the last thing is we're going to convert that circuit to a circuit of OR gates using, NOR gates, using the technique we talked about last time, which is to say we just convert all of the gates and then we invert the input, the literal inputs, at the odd numbered levels. So we'll start here on the back end with 2 NOR gates. Now that's at level 4, which means none of those inputs get inverted. AC, A prime, C prime. Let's see. And then that feeds into not an AND gate because we're converting them. Another gate. So that one takes these two. And we have another NOR gate which takes B prime and D, but this is level 3, which means it's an odd number level, which means that those input littles get flipped over. We're going to have B and D prime. Then we have level 2, which had three gates. First one takes that first NOR gate. Level 2 is even, so we leave the input literals alone. B stays B and D. And we have A and C prime, so A or C prime. It's going to stay A or C prime, then A prime or B prime, or C is going to stay A prime, B prime, C. And then finally, the last gate is converted to NOR. It has no single input literal, so there's nothing to change, despite the fact that it's 1, which is an odd number gate. And that gives us our output F. Cool. So there we go. Here's our realization of that circuit using three input organs. Right on time. All right. Any questions about that? All right. I think it's a pretty cool example. That's a good, it does a good job of sort of illustrating every step in our process. We had some constraints, right? We had to work with NOR gates, which of course informed our design decisions from the very beginning. We had to deal with the 3-input fan-in situation, which required us to do some Boolean algebra manipulation to get it where we're going. And then we did this stuff, man. Cool. Any questions about this example? You know, it's a good example. It takes like the whole class to do, right? All right. So, if there's nothing else, I apologize for the confusion. We might just keep having class in here because I like it, and you know, chalkboard doesn't break. So be on the lookout for that. Obviously, we're just 2 hours down, so plan on coming here for class next time. Okay. All right. So, if there's nothing else, we'll see you guys on Friday. Don't forget, Unit 5 is due today, due tonight. Exam number 1 is due tonight. Yeah, Unit 7 is available. Unit 8 assignments available. I'll see you guys on Friday.